And yeah, welcome. I'm happy to see so many attendants here. So I would like to give you, or we would like to give you, a bit of an update on what has been going on at Rigaku about electron diffraction, and in particular about the Synergy-ED, our dedicated electron diffractometer. It's been, I think, more than a year since the last webinar about it, which was the launch webinar, and a lot has been going on. We've introduced new features, we've had nice scientific results, and we would just like to give you an update on some aspects of this. So let me give you an overview of what we are going to do. First of all, to get everybody on the same page, I will give a bit of an introduction to both electron diffraction in general and, of course, specifically to the Synergy-ED. Next, Christian will give you a bit of an overview over some scientific highlights, some research results from data taken on the Synergy-ED that led to high-ranking publications that cover quite a broad range of scientific topics. And then we go into some new stuff that Kai will report, which is mostly about studying hydrated samples by the means of using cryotransfer techniques for electron diffraction. And finally, to wrap up, I will give a bit of a sneak preview of features we are at the moment implementing or have just implemented, and which we believe extend the capabilities of the Synergy-ED significantly. So let's start with a bit of an introduction. Here you see our range of XtaLAB Synergy instruments, starting from a benchtop instrument all the way to a high-end custom instrument and an illustration of a synchrotron, which we're not building yet. But for all of those, there's a certain limitation that with X-rays in general, it is relatively hard to go below a size of roughly 1 micron with your crystal size to get a sufficient signal for structure solution from a single crystal, unless you go for exotic techniques like free electron lasers or maybe some serial crystallography at synchrotrons. But by default, this is sort of a barrier. Electron diffraction, on the other hand, has this barrier from the other side. So crystals that are larger than 1 micron, or significantly larger, essentially turn out to be sort of a beam stop for electrons, because electrons interact with any sort of matter up to 5 orders of magnitude more strongly than X-rays. So electrons allow to study crystals as small as this one shown here, which is around 300 nanometers across. So crystals that are in the submicron range down to even tens of nanometers can be studied very nicely with electrons due to the strong interaction, but also because electrons, if normalized to the amount of information you get from elastic scattering into your Bragg peaks, cause way less damage to any sort of crystal, which allows you to get a full data set from single or a few grains without causing too much radiation damage. And if you look at this whole spectrum, it becomes clear that X-ray diffraction and electron diffraction are complementary techniques which allow you to study crystals over a whole range from the nanoscale to hundreds of microns. And we now provide you with a coherent portfolio of instruments to cover all of this. So let me introduce you a bit to the basic idea of this electron diffraction techniques and how those are done in the Synergy-ED and in general. So the way electron diffraction is mostly conducted now for structural solution is to just replace X-rays by electrons in a very familiar scheme of rotating a single crystal inside a continuous beam with concomitant shutterless data collection on ideally a hybrid pixel detector. One thing that is important to note at this point is that this is not what electron microscopists mean when they say electron diffraction or electron crystallography, because in electron microscopy, what is usually meant by this is that you rotate crystal very carefully to a low zone axis and then get one of those beautiful, strongly dynamical diffraction patterns that you see from that. They look good, but they are very hard to use for structure solution due to strong dynamical effects. Whereas here we really continuously rotate the crystal in the beam just like you would do on an X-ray diffractometer. This way of doing it has actually been around for quite a while, but has seen a bit of a resurgence starting from the 2000s in several European and later on American groups. And those groups have sort of invented it in parallel and a bit simultaneously, which leads to the bit odd situation that this technique is known under a lot of different names and abbreviations. All those refer to slightly different variations, which in the end are more or less equivalent. And the community has now very much settled on the two names, 3D-ED for three-dimensional electron diffraction and micro-ED for microcrystal electron diffraction, which can largely be used interchangeably. I'll refer to it as 3D-ED in this presentation, but any is fine. And so far, this has been applied to, well, pretty much everything that forms crystals and diffracts. So pharmaceuticals, small organics, metal organic and covalent organic frameworks, zeolites, minerals, proteins, peptides, natural products, and so on. I think natural products are a specifically interesting example, as the amount of sample that you need for an electron diffraction experiment is really only minute. So if you only have a little amount of sample available, it's an ideal technique. A drawback is that so far it's something that's not too easy to do because it has to be conducted in adapted transmission electron microscopes that are equipped with everything you need for it, which reduces this to just a dozen of research groups which are able to do it in the first place because they have the necessary skills and equipment in both crystallography and electron microscopy. And we wanted to change this. So in 2020, we teamed up with another company, with JEOL, to form a joint venture to develop a dedicated electron diffractometer. And JEOL, well, you may know them from their NMR machines and also from all sorts of electron beam instruments, TEMs, SEMs, FIBs, and so on. And then they are not only almost next door neighbors of Rigaku in Tokyo, but they also provide us with nice complementary expertise, because Rigaku contributed to this project all parts that pertain to crystallography, like a very good diffraction detector, all the control software and the crystallographic software for it, the scientific support, the user training, etc. And then everything that is electron specific, like the electron gun and the electron beamline, was contributed by JEOL. So the expertise of those companies really ideally matched to build the XtaLAB Synergy-ED, which you see here. It's a dedicated electron diffractometer, which is specifically made for crystallographers and does not require you to have any skills in transmission electron microscopy, which is a truly novel part about it. Its hardware design is highly optimized for 3D electron diffraction. It provides a seamlessly integrated user experience, including both hardware and software, all the way from instrument control to the structure solution. We'll see that in a bit. We have now 4 of them installed in our application labs in Europe, in the US, and 2 of them in Japan. And we expect to have 8 customer installations by the end of 2023. So now let me just briefly show you what I mean with a seamlessly integrated workflow. The steps you have to take for a 3D-ED experiment is, first of all, to look for suitable crystals. And because these crystals are so small, you cannot see them under a light microscope anymore. So the only way to find them in the first place is to have screening capabilities in the electron instrument itself. And of course, we have that. And the screening is already done within Chrysalis Pro, our software for instrument control and data processing, which you may know from our single crystal X-ray machines. So it's the very same one, which has a screening functionality, but then with a click of a button also allows you to collect the data and then using the AutoChem interface directly solve the structure, or to interface with structure solution softwares such as OLX2. And instead of just discussing images, let me walk you through the workflow of a 3D-ED experiment in a Synergy-ED by some short videos. And let's start with a bit of sample preparation, because of course, with those small nanocrystals, this is quite different from what you might be used to and when you think of a single crystal experiment. So here are some necessary tools that you will need, and also a sample holder rod. We will discuss that in a bit. So our colleague Ito-san from the Tokyo Applications Laboratory is just taking a minute bit of powder that you would otherwise use, for example, in a powder X-ray machine. This powder is a test sample which is already nicely microcrystalline. Otherwise, at this stage, you could grind it a bit further with, for example, another glass slide on top or in a mortar, different ways. And then the next thing that you need to do is to apply this powder to a TEM grid. And this is what is going on the tweezers right now. These are little discs which are comprised of a copper mesh, 3 millimeters in diameter, and are coated with an evaporated film of thin carbon, which is electron transparent. So one way of getting your crystals on it is just to dip it into the powder. They will stick on it. They're a bit of too big ones, but you can just shake them off, as shown here. And now you'll have deposited just a thin layer of powder, which also will likely include some small enough nanocrystals on your grid. As the next step, this grid is mounted into this piece here, which we refer to as a sample holder or sample transfer arm. This is the part that in the end will move this grid into the vacuum of the electron diffractometer. The grid is mounted to the tip of it, just a very straightforward way into this cradle. And then using a retainer piece that you see here, which is closed shut, it is held in place so that it just doesn't, well, fall off when you rotate the grid during data collection. As you see, this is a very straightforward process. And in the end, well, you have your grid here, you have the nanocrystals on the grid. All of this is sitting on this arm. And we'll see later on how this arm will be inserted in the Synergy-ED. But let's first have a look at the software again and how our workflow looks like once you have the sample in and you have fired up Chrysalis Pro. So what you see here is the screening interface, which we also call the visual mode of the Synergy-ED. Down here is an electron optical projection image of the entire grid, which is the same as you've just seen before in the light microscope and allows you to correlate the electron optical image and the light microscopic image to each other. You can navigate the stage to positions on this grid just by a point-and-click interface. Now here, this is a close-up of a certain selected section on this grid where you can see the sub-micron size nanocrystals. This circle here has a diameter of approximately 4 microns. So you see that those crystals are in a nice size bracket. Especially this one seems suitable because it's even a bit translucent, so it seems to be pretty thin, which is a good thing. You have to think a bit the other way around for electrons. So you don't want big, thick crystals. You want small, thin crystals. So this one looks good. And also in this window, you can navigate using a point-and-click interface, and you'll see that now. So the way to move the stage of this crystal is just by simply clicking it. And the next step is to check if that crystal diffracts at all. And it's only a push of one button to switch this whole electron beam line from this visual screening mode into diffraction mode. There's only one electromagnetic lens in which the current needs to be slightly changed to switch between those two modes. It's a very straightforward process without any sizable hysteresis. And the next thing after you've checked that it diffracts at all is, of course, to center it on the axis of the goniometer. And again, this is done the same way as in an X-ray machine. You tilt the sample by a certain amount, and then again, using a point-and-click interface by repeatedly clicking on it, you will center it on the rotation axis of the gonio, and now it's ready for data collection. And this is what we see next. And as you will see in this step, the data collection is extremely similar to an X-ray machine. So you will be presented with this dialog window here, which you might have seen before. If you've ever used Chrysalis Pro, you set your data collection parameters like the scan width, the scan range, and the exposure time. And one key thing that is different from an X-ray experiment is the measurement time. So we are speeding up the measurement, but not by too much. So you see on this wall time clock that within a minute or two, you fully collect the data from this single crystal, you also see that in the background, the data reduction has already started, and even the structure solution and refinement has begun. And ideally, by the end of the data collection, sometimes even during the data collection, you'll have a structure solution or first structure solution popping up here. Of course, if this does not work, or if it needs some more manual work, you can directly fire up your favorite structure solution software. We usually use OLX2 for this, and by click of a button, you can download it and work further on it. So this was a quick overview of the workflow, and I hope this illustrated how easy it is to collect electron diffraction data, especially if you're already used to Chrysalis Pro and our X-ray instruments. Now, just a quick word about the hardware that I promised you. So here's of course, only a rendering of how the instrument looks from the inside. What we have is a JEOL, it's called an electron column. So that's a combination of an electron gun here at the top, and then a beamline that is comprised of a set of electron lenses and apertures, which guides the electron beam on the sample and then further on projects it onto the detector. We have a hybrid pixel detector made by Rigaku. It's the XtaLAB. It's essentially the same model that we are using on the X-ray machines, just adapted for in-vacuum use on electrons. It's a hybrid pixel detector, which is single electron sensitive and has absolutely no background. It's really the best you can get for getting very accurate intensities from even extremely weak data. And this, of course, is all important, especially if you have radiation-sensitive samples, where you want to make sure that you never use more dose than you absolutely need. Finally, we have this sample stage here, into which you insert those sample transfer arms that you've seen earlier. And we offer, or it is compatible with a wide portfolio of different types of those sample arms. The one we've seen before is a quite simple one. We'll later on learn quite a bit about cryo transfer arms and when to use them, but there are also general cooling holders, heating holders, holders for inert transfer, and other options which are directly compatible with the Synergy-ED. And in our application labs, we have by now solved well more than 300 structures. Here you see some crystallographic figures, some statistics of those. So we cover a large range of unit cell length, including proteins, so up to 150 angstrom. It's the biggest one we've measured so far. Here you see, well, we can cover all crystal systems, of course. This is quite interesting. These are the kinematical R1 values. With kinematical, I mean that in the refinement that yielded those values, we use the kinematical approximation of only single diffraction events. This approximation is relatively bad for electrons, which leads to these R factors being systematically higher than for X-ray. So the median is about at 17%. This is just a standard property of electron diffraction, nothing too specific about the Synergy-ED or the systems we've been looking at. And this is just the typical scale for electrons. Again, this is a systematic effect. This does not necessarily have to do with bad data quality. One more word about this, I'll say at the end of this webinar. And finally, about the systems that we studied itself, well, we cover a good range of the periodic table, and we also cover different groups of samples, now even proteins. We just got started with proteins, so the slice of the pie is so small that you can hardly see it, but it will expand soon by quite a bit. And of course, this is just a statistical overview, and you will probably be much more interested in concrete examples. And for this, I'll now hand over to my colleague, Christian, who will present you some research highlights from the last year.
Thank you very much, Robert. So hi, I'm Chris. I'm an application scientist at Rigaku Europe SE, and I have been involved in the publication of a couple of our data sets we collected over the last 1.5 years. And I want to start with these. This is an overview of all the publications we got so far. And you see quite numerous, and the number is rising. And I would like to highlight some of them. First off is this first, or one of the first and one of the most important publications we got so far, with Nicholas Pierce and from the Champness group in Birmingham. And it got pushed up to Nature Communications by the support of Synergy-ED. It's an editor's highlight, and it was published all over the internet, and maybe you already have seen it. It contains this rhotoxane structure, and these rhotoxanes are very, very challenging samples by themselves. They have a huge, they are vast structures with a huge atomic weight, 3,500 Dalton, mostly organic. They have very low symmetry, P1 bar, and they just don't crystallize very well. So they result usually in extremely small crystals. At the point when we were included into this project, synchrotron data on the largest crystal they could find were already present. Therefore, if you look into the supporting information of this publication, you can actually find a very nice comparison between the synchrotron and the Synergy-ED. They took the largest crystal they could find, a few micrometers in thickness, and this is the result they got from the diamond light source synchrotron. As you can see, they got a resolution of 1.25 angstroms and good completeness, R value beyond 30, and according data. And with this data, they were able to refine a best guess model. The atoms were placed in the expected positions from theoretical calculations, and they then refined this best guess model by using quite a lot of restraints and constraints. And well, they got a result. It was good enough. But then we got data from the Synergy-ED, and as you can see here, we not only used smaller crystals, we used the crystals smaller by a couple of order of magnitude, by 1 or 2 orders of magnitude, and they were really thin. These crystals tend to form very thin plates, and this is actually quite preferable for electron diffraction. Nevertheless, we got about twice as many data. We could get the ab initio structure solution, including the before missing anion. We were able to refine it with very little constraints and restraints, and we in the end got a better R value, but despite of the kinematical approximation or the kinematic refinement. Therefore, one could say with good conscience that the Synergy-ED outperformed the diamond light source. Next up is this publication on metal organic frameworks from the Kitagawa group. They exchanged the cation for this framework here, and kept this ligand linker, thus tweaking the ligand orientation and subsequently changing the pore structure and also the gas interaction of this kind of MOF. At the same time, the metal organic framework changed the pi stacking interactions and subsequently its conductive properties. These structures have not been available before with other techniques, and these structures represent the huge interest group in Synergy-ED. About 1/3 of the samples in our lab are nowadays metal organic frameworks. Next up is this publication from the Kahlenberg group in Innsbruck. It is concerned with this ceramics structure and solves a mystery on this particular ceramics. This is concerned with this orientation here of the sulfide group here on the left-hand side. On the left, in the left depiction, you find the assumed triclinic group, where this sulfide group is always pointing down, and turned out with the data from electron diffraction that in fact, and every other time this one is pointing upwards, thus leading to this gamma this different orientation of this ceramics. This ceramic sample is representing a whole field of materials research samples. These kind of samples are very well suited for electron diffraction. They come usually as powders with quite small particles. They diffract like crazy. You can see this sample diffracted up to resolution up to 0.60 angstroms. They are very resistant when it comes to sample decay in the electron beam, and therefore they are excellent samples to work with. Then next and last up is this publication from Thomas Mies and colleagues from the Imperial College in London. This is on organometallic compounds with calcium in the center, and it has coordinated solvent on it, ethanol and water. What we were able to observe during this experiment was that for the first few crystals we did an experiment with was that these contained some water coordinated to the calcium, and then later on in the progress of measurement for the last couple of crystallites, this solvent was gone. It resulted in a slight change of the unit cell parameter, and of course we couldn't find it anymore in the structural solution. And this is quite an interesting feature of this structure. However, of course, we would like to be able to control this behavior in a more better fashion. And this is what we will be concerned with in the next part of this talk, when we talk about studying samples under cryo conditions.
Okay, and at this point, I will take over again. Yeah, as Chris just mentioned, sometimes desolvation is an interesting phenomenon, but well, more often than not, you are not interested in how the environment of your diffractometer changes unavoidably your sample, but you'd rather want to have your sample preserved in its native state. And for solvated or hydrated samples, one good way of doing it is just by freezing your sample outside the vacuum, and then in the frozen state, introduce it into the vacuum of the diffractometer. Of course, the vacuum itself is unavoidable for an electron diffractometer, as the electrons would just stop in air. And then you measure it under these cryogenic conditions while it is protected. So to do this, in our diffractometer, we have this advantage that we keep the samples on those sample arms. So we can, instead of using this room temperature sample arm that we've seen in the video earlier, use a slightly different model, which differs in that it has this dewar mounted here, which is relatively small, but has a very long hold time. And this dewar is thermally connected through a rod in here to the tip of the holder, where in a similar way to the room temperature holder, the sample grid with the powder on it is held using a simple retaining mechanism. And the way you prepare the sample here is that you freeze the grid with the sample in liquid nitrogen or liquid ethane in case of biological samples, and then insert this grid into the holder, which also has been pre-cooled. And one small but extremely important feature that this holder will also have is that it has this tiny shutter mechanism. So it's a shutter that can be operated from outside and can close above this little sample space here. And this is important for the reason that if you have the sample in here, you need to transport the holder from a protected environment with cold nitrogen vapor or even liquid nitrogen, where you do the sample transfer into the diffractometer through air. And if you just walk with this thing through the lab with humid air and it's cold, of course, it will form some frost. And if the frost forms on the sample, it will kill it and just the electrons can't go through anymore. With the shutter, it is protected for long enough to put the sample from your transfer system into the diffractometer. And how this looks like, we'll see again in a short video. So this is our laboratory here near Frankfurt. So Synergy-ED for real. And what I'm doing now is take this holder from this little black transfer station, which has this small dewar here too, which is where you can load your sample into the holder under cryogenic conditions. It is now inserted into a sample airlock system, so not yet fully into the diffractometer, but into a pumping airlock, which within a minute or two reduces the pressure by almost 10 orders of magnitude around the sample tip. This takes a minute or two, as I said, and then afterwards you get literally green lights for fully inserting the sample into the diffractometer by rotating it, which opens a gate valve mechanism. And now it is inside the diffractometer at the interaction point with the electron beam. As a matter of best practice, the next thing I'm doing here is to top up this dewar, which will maximize the holding time, which can be up to 10 hours in theory, which is honestly something we never really need, but easily enough for any sort of measurement. And as a final step, I'm opening this little shutter that you've seen before so that the electrons can now hit the sample. And next we see another quick video, just a quick single shot video from the data collection. So here you see Chris operating the instrument. And what you may observe is that when Chris is not moving the sample stage, the sample still moves a bit. It drifts a bit because after insertion into the diffractometer, the temperature will usually still be a bit unstable for about 50 minutes. But until that, you can still use the time to just screen some grains, just find ones, some that diffract well, and then by the time the drift has ended, you know already where to go and which ones look promising. And here Chris has found one already. I think it's hard to see via Zoom that the scale of this plot is decreasing more and more, which means that the temperature gets more and more stable, but you may also observe that the drift becomes less. Still, Chris has plenty of time to do a very, very accurate centering of the crystal on the stage rotation axis so that he can do a very large rotation range scan. So here we go. Now he switched to this diffraction preset. So again, we see this is a really very nicely diffracting crystal. I think now he does one last check if it didn't drift away from our region of interest. Turns out it didn't really. And we can start the data collection just the very same way as before. And now, yeah, we just see the automatic data collection running. We see the progress of the concurrent data reduction and structure solution. And we will also see that this works quite nicely. And well, it's tyrosine again. So it solved it automatically without any user intervention. Of course, it's not a sample that's particularly exciting, but there are very exciting samples that you can study by the means of cryotransfer. And this is what Kai will now tell you about.
Thank you, Robert. I'd like to introduce myself again. I'm Kai Truong. I'm also one of the application scientists here at Rigaku Europe SE, working on X-ray, single crystal X-ray and electron diffraction. So I'm now filling the gap which has been talked or shown before by Chris, where most of the samples have been either measured at room temperature with a room temperature standard holder or just by normal cooling. With our cryotransfer holder, we were able to study even samples which are hydrated or solvated, as Robert has said. So let's have a look. So one of the samples, one of the first ever measured samples with our Synergy-ED was tray hollows anhydrous, yes. And there we could get the structure, and now with the cryotransfer, we were interested in the hydrated sugar compound of tray hollows. And this is what we did. We did first a measurement under high vacuum and room temperature, and we could see that it loses diffraction power. So as you can see here from the diffraction image, we didn't really get many diffraction spots. It was not enough to solve the structure itself, but it was enough to solve or to find the unit cell in the CSD by just checking it either in the web CSD or the local database. And it was the anhydrous form. Now, if we now use our cryo transfer holder and measuring at 170 Kelvin under high vacuum, we could see that the diffraction or the resolution limit increases rapidly. It diffracts well to almost 0.8 or below, even below 0.8 angstrom. We could get the dihydrate form, as you can see here. We have also done a temperature-dependent measurement on this one. This was one of those samples where we did it, and we could see that around 260 to 270 Kelvin, it goes to the anhydrous form. So with our cryo transfer holder, it is not only possible to do these low temperature measurements, but we could even study to up to 100 degrees Celsius data collections if we are interested. Another example, so we are not only possible to do it on really small organic molecules, we could also do the same with metal organic frameworks. Again, at vacuum, under high vacuum and room temperature, we almost see no diffraction. If we now use our cryo transfer holder, it diffracts beautifully, even to 0.6 angstrom. We could get the immediate data. Well, now in these cases, we have seen that they lose the hydrates or solvates or whatever, but there's another possibility what could happen. And this is with these samples from our collaborators from Ruda Bošković Institute in Croatia. They've sent us some samples and they knew via several characterization methods that this compound that they have sent us, it was organic co-crystals featuring thymine and 2,6-diaminopurine, that it is a dihydrate or at least some hydrated co-crystals. So when they have sent us these samples, we didn't have our cryo transfer holder yet. So we were just measuring it with a normal standard cryo holder, and we could see in this case, it is a crystal to crystal transformation. It loses the water, but it doesn't lose the crystallinity. So as you can see here on the top, it's a 2-to-1 stoichiometry, and the lower part a 2-to-3 stoichiometry. If we do now the same with the cryo transfer holder at 100 Kelvin, we can keep the water molecules in its crystal structure. They don't lose it. They diffract beautifully to 0.8 angstrom, and these are the results. Another example which showed this beautifully, that they usually don't lose the crystallinity, is this one with this fungicide manep. At room temperature, again, it loses the water. We have these sheet-like coordination polymers. But again, when we cool it down to 100 Kelvin, with the help of cryo transfer, we could keep the water. This sample was especially very interesting for our collaborator from University of Wuppertal, because this fungicide has been known already and used in agriculture for the last 70 years. And they have tried to get at least the X-ray structures or single crystal X-ray structures since the last 20 years. And for us, it took us just a few minutes to get even both structures, the anhydrous and the hydrated structure. So this is one of our routine now, that we always screen first at room temperature, see if it loses crystallinity, or maybe if we are lucky, we get another structure. And of course, we measure with the help of the cryo transfer, we measure at 100 Kelvin. And in this case, we could see that it really gives us a lot of benefits if it's maybe just by reducing beam damage if we could also increase or improve the resolution. We can stabilize and protect our samples with the help of cryotransfer. And in some cases, if you have disorder, you could also reduce it. So next, Robert will continue and talk about ongoing developments for our ED in the future or past.
Or present, in fact. Thanks, Kai. Yes, so I would just like to give you a bit of a preview to what might be our next topic webinars on the Synergy-ED. So just some stuff that we are doing right now and that I think might be of interest to many of you. So some may wonder, can the Synergy-ED do proteins? And the answer is, well, yes, absolutely. So electron crystallography on proteins is something that has also now been around for almost 10 years or so. It needs quite different preparation techniques from small molecules or also from macromolecular crystallography with X-rays. The techniques are usually more borrowed from cryo-electron microscopy, so they involve vitrification and liquid ethane. I'm not going to go into details about this. We have run test experiments where we did this and then prepared nice thin lamella from these microcrystals using focused ion beam milling, cryo-focused ion beam milling. So from those crystals, you can just cut this thin lamella, which puts it in the perfect thickness range for electron diffraction. Here we have the just a close-up from the resulting crystal structure. It's tomatin, so just a test case. We could directly process this into Chrysalis Pro in the standard macromolecular mode to decent resolution and solve this by molecular replacement. We can observe some hydrogens in the structure. Observing hydrogens, I should say, is tends to be easier with electrons than with X-rays, as electrons have higher scattering factors or relatively higher scattering factors at low atomic numbers than X-rays. So this worked out here. And one thing or one feature of the Synergy-ED I would like to highlight in this context is that it has a settable crystal to detector distance, not by means of moving the detector physically, but just thanks to the projection electron lenses that sit in between the sample and the detector, which allow you to change the virtual crystal to detector distance just by means of electron optics. And for proteins with their long axis, in this case 150 angstrom, we could dial this up to 1.8 meters. We can even go higher, up to 3 meters, I think, and separate the spots even along this long axis nicely enough that with the very good integration techniques implemented in Chrysalis Pro, we can get really good intensities from those spots while keeping a detector resolution limit of 1.2 angstrom along this long axis of our detector, which has a pretty large area. The next topic that we are at the moment working on quite a bit is increased automation of the measurement process. So there are a lot of those crystals on one grid. And of course, the question would arise, can't you just automate this process more of measuring all of them? And in fact, we haven't shown this to you yet, but we have a quite neat queuing feature built into Chrysalis Pro where you set up a measurement queue of many of those crystallites and then have it done the collection in an unattended way for up to hours if you set up sufficiently many data collections. It has some features like correcting for stage drift that might have occurred. And there are several use cases for this queuing. The most obvious one being that, especially if you have only triclinic symmetry, because of the single tilt goniometer that's available only with a tilt range of total 160 degrees, you might not get sufficient completeness from a single grain to get the structure solution. Or your sample might be too radiation sensitive and just die before you have sufficient completeness. And in all those cases, you need to merge many or at least two crystallites or the data from them together. We have a nice graphical tool for this in Chrysalis Pro that gives you the merge completeness for given combinations of data sets. And you can set this up from those queues of many grains. Another maybe even more exciting use case is if you don't have the same grains, but if you have various polymorphs or impurities on your grid that you would like to screen and to disentangle. So think of a powder that is just a mixture of different phases, and now you can measure each grain of that powder separately. And this is exactly what these kind of automation features allow you to do, to then just tell which of those crystals is which, and even solve structures of each type separately. And as a very final outlook, one thing that you might have heard about and that I also was alluding to already is the modeling of the dynamical diffraction. So I mentioned already that the kinematical approximation of only having a single diffraction event for each electron is not quite valid due to the strong electron interaction. And to get a really good modeling of the data and concomitantly low R values, you need to do the modeling including dynamical diffraction effects arising from multiple scattering of electrons in your crystal. And this is not only a nuisance, but it's also an asset, because this dynamical diffraction breaks the Friedel symmetry and hence allows to determine the absolute structure of your molecules. So here, well, it's again tyrosine, but I can assure you it also works for a large number of other molecules, that if you refine both enantiomers against your data in a dynamical way, you will see from the R values which one is the correct structure. And that's a new and I think pretty unique feature. XtaLAB Pro can directly interface into YANA 2020, which you may know, it's a structure solution and refinement package, which allows to do exactly this dynamical diffraction modeling. And XtaLAB Pro can prepare input files in a very particular format that allow for a very hassle-free workflow that includes dynamical diffraction. And we are almost done now. Just one thing I want to point out is that we are now also offering a 3D-ED measurement service for data collection in our various application laboratories. We provide you with structure solutions and scientific support if desired. But in any case, you, of course, get the raw data and processed intensities and full access to the XtaLAB Pro software for data processing. See here for some more details. And very finally, I would like to announce that during the DGK conference at the end of March, we'll have an open house here in Neu-Isenburg, close to the conference. Please register here for a lab tour to meet us and see our instruments. That's it. Thank you very much. And well, we are now hoping for a lot of interesting questions.
Thank you very much, guys. So we do have quite a number of questions. I've noticed that some of them you answered as we went along anyway. So the highest upvoted question is about absolute configuration determination, which you just covered. I don't know if that was a sufficient explanation for you, Marius, but if you would like to ask again, I'll just mark this one as done. If you want to ask again, if you need any clarification, please do. So I'll just move on to the next one. So comments on reliability of anisotropic refinement would be appreciated, and also the associated standard uncertainties on, for example, interatomic distances. And the same person has also asked about hydrogen atom visibility and can they be refined?
That's a couple of questions.
Yeah.
Well, so generally speaking, it always depends on the data quality and the qualities of your particular sample. I assume that you are referring to a kinematical approximation, because if you do the proper dynamical refinement, all of these qualities that you are addressing, the anisotropic refinement, everything should work as usual, as with X-rays, as you are used to it. It should just fall in place. And then there are some features that you need to account for when you refine electron diffraction data with the kinematical approximation. And this is that electrons interact with the electrostatic potential of the molecule. And this means when you have ions in your structure, they will interact with the electrons significantly different than the atoms might otherwise do. So the atomic scattering factor not only depends on the atom type, but also the charge of the of said atom. And this again can affect the anisotropic refinement. So it can happen more regularly that you have NPD, non-positive defined or physically non-meaningful atomic vibrational parameters. However, this does not terribly this does not really affect the interatomic distances. Usually the interatomic distances you find with electron diffraction are quite accurate. I'm not aware of any issues we ever had with this.
One interesting thing to keep in mind that they are accurate, but they might not be the same as for X-rays, because of course electrons interact with the full Coulomb potential that is also determined much more from the nuclei and not from the electron cloud. So for example, the CH bond length for electrons is larger than with X-rays, because let's say the density is really of the hydrogen is really closer to the proton.
Yes, and this is also referring to the last part of the question with the hydrogens. We can see the hydrogens pretty well with electrons. We can in fact see them better than with X-rays.
Yeah, but of course, yeah, this is it's a very complex question, because as Chris already said, it depends a lot on the crystal quality, and with electrons you tend to study systems that are difficult and that do not form nice crystals, because otherwise you would use X-rays to begin with. So yeah, it really depends.
Thank you very much. So next question that's been voted to the top is, for the multi-crystal automation, will we need new hardware, or will it be available in the current Synergy-ED?
It's a complete software thing. There's no yes, yeah, that's
all
the
you
answer.
Yeah,
it's software automation.
Yeah. So the next one is also a hardware question, which is, are you planning to offer precession electron diffraction capability?
No. Simply because for the type of measurements that the Synergy-ED is specialized on, in our opinion, it does not bring with itself significant advantages. The reason is that we are not using the discrete stepwise technique of collecting data, where you would just move to one certain collection angle, take a snapshot, move further, take a snapshot. But we do a continuous data collection, which also gives you integrated intensities by having in electron language, I'm sorry, continuous integration through the excitation error of your reflection. In precession electron diffraction, you achieve the same by processing the incident angle of your beam for given discrete orientations. This leads to a slightly different way of data integration, but in the end, the accuracy of the integrated intensities, also with regards to dynamical effects, is comparable. So we do not see much advantage in precession capabilities for our case. Of course, there are cases where precession is great, but not for what we were just discussing.
Yeah. So they've jumped a little bit, but the next one I was going to ask, I noticed that electron diffraction data have relatively low completeness, possibly due to the restricted rotation of the sample in the vacuum chamber. How would you assure that data you're collecting has sufficient completeness for good refinement and publication?
So, well, two approaches. For once, we use mostly tomography holders that allow us for a very wide sample or angular range to access with the sample, and thus we can get good completeness from the start. And if this is not sufficient, we can merge data from different crystallites. 2 or 3 data sets should be enough to get a structure solution from even the lowest symmetry compounds.
Yes. And you usually, even for monoclinic crystals, get enough data to solve and easily refine the structure from a single crystal. because we usually can measure over 160 degrees wedge, even in our standard configuration. We're inside the diffractometer, for example, less spatially restricted than in typical electron microscopes. So there's more space around the sample, and we use narrow holders and so on.
The next question is there a limit? So what is the limit for the vapor pressure for the vacuum seal? Would it be possible to introduce, for example, terpenes into the system and still get readings? Also, could you freeze compounds that are liquid at ambient temperature on the sample holder and work from that? And thank you very much for the interesting presentation.
So in the column, there has to be, like in the diffractometer column, there has to be high vacuum, down to ultra high vacuum. So it has to be absolutely vacuum compatible. And you have to have some way of preserving your samples, either using low temperature or maybe at some point using some encapsulation techniques of the sample. I didn't quite get the second part.
The second part was referring to solvents that are liquid at room temperature, whether you can
So essentially crystallizing on the grid.
crystallize them. Yes, you
Into
can.
the
So icing is a common feature. And this means that we can have crystalline ice on the sample holder. So it obviously applies to at least some of the solvents. And then it depends on the particular solvent that you are using, whether it will be stable at low temperatures under this high vacuum.
Yes. So as a particular example, water. For water, you could plunge freeze it into liquid ethane. In this case, it would just vitrify. It would not even crystallize. It would vitrify, just perfectly emulating the conditions as if it was still liquid. This is just a widespread technique from how all of cryo-electron microscopy works. You just cannot use nitrogen in this case because this would cool it too slowly. But cooling in ethane might help for water. I don't know how this is with other solvents, but I think there are studies on that too. I'm just don't know the details right now.
Just depends on the solvent, I guess. Right.
Okay, we're almost out of time. So there's one more upvoted question, which I'll ask in a second. The rest of the questions, some of them were answered during the presentation, but we'll try and answer whatever's left over and put the answers onto our forum. So the question I will ask is, are there a lot of changes to the data analysis procedure when moving from X-ray to electron diffraction? Does the diffractometer allow for any kind of electron beam manipulation, focus beam, beam shift, etc.? Does the detector have any major distinction from common electron detectors?
The common electron. Okay.
I think the answer is yes.
But
very short.
Yes.
Yeah, I think to all of the questions. Yes. Yeah. So the data analysis, specifically as we do this continuous rotation method, the data processing is by and large the same as for X-ray diffraction, and it's done using the very same pipeline in Chrysalis Pro or any other software that you fancy. It is worthwhile to tweak some of the standard parameters, for example, in the determination of the space group. But this is just, minor tweaks. The overall workflow is exactly the same. Then about the beam manipulation, other electron optical manipulations, you have some flexibility that, in our opinion, is necessary and makes sense for electron diffraction. It's not, and it's dedicatedly not an electron microscope where you can have huge ranges of parameters. These hand panels can do everything and manipulate everything, because apart from this high complexity and high required skill levels, this also would cause instabilities of calibrations, etc. And these things that we do not want and do not have in our system. So yes, we provide flexibility, like how big is the beam, how big is the region that you want to diffract from, of course, how strong is the beam. All of this can be set and is stable, but only over a certain range. For example, one thing which we cannot do in the same way as a TEM is having strongly convergent beams, because there would simply be no point for a crystallography experiment. And then finally, about the detector, well, it's a diffraction detector. It's it's the same type of detector that you would have on an X-ray diffractometer. It has many fewer pixels than an electron camera, so it's less suited for real space images. It has an extremely high dynamic range, is absolutely background free, and totally optimized for collecting diffraction data. So the technology behind this is very different from, say, a monolithic direct detector like you may know from cryo-electron microscopy, like a Gatan K3 or a Falcon or a DE16 or what have you. In terms of most of its properties, it's on the opposite end of cutting-edge detectors, I would say.
Okay, so we're a little bit over time, so I think we'll call it there. Just like to thank you all for attending and thank Chris, Robert and Kai for their presentation again. We will have another topic webinar in approximately 2 months, which will go on to our usual channels to promote it soon. We don't have the materials ready yet, so I'm not going to say any more than that just now. That's all for today, so thank you for joining us and have a pleasant day. Thank you, bye-bye.
Thank you.
Bye.
Bye.